Welcome to The Explainer. Today, we are tackling a pretty massive electrical engineering challenge. I mean, how do you even measure something you can't get close to without, being instantly vaporized? Let's find out.
Okay, so we're talking about those huge high-voltage transmission lines you see crisscrossing the country. Some of them are carrying an incredible 400,000 volts. Now, just to put that into perspective for you, that is more than 500 times the voltage that's coming out of the outlets in your home. The magnetic field alone is so powerful that you don't even have to touch the line for it to be incredibly dangerous.
So how in the world is it done? I mean, you can't just whip out a standard multimeter, right? Its maximum range is maybe 750 volts, so it would just be toast, instantly destroyed. This problem, it required a much more clever approach. And engineers, well, they came up with two really specialized devices to solve it.
And here they are. Our heroes for this explainer are two very special types of transformers. You've got the current transformer, which everybody just calls the CT, and the potential transformer, or PT. Each one of these has a very specific, and let me tell you, a very important job.
First up, let's tackle that massive flow of electricity, the current. To do this, we're going to need our first device, the current transformer, the CT. Let's see how this thing ingeniously tames the insane amount of amperage flowing through these giant power lines.
So the whole job of a CT isn't really to measure the current directly. Think of it more like a translator. It takes this huge, unmeasurable current, let's say you've got 1,000 amps flowing through that main line, and it precisely scales it down to a totally safe and manageable 5 amps. And that's a number that any standard ammeter can read without a problem.
The principle behind it is all about magnetic induction. You see, the main transmission line itself, it acts as the primary coil, basically just a single loop or turn. As all that current flows through it, it generates a powerful magnetic field. That field then induces a brand new, much smaller current in a secondary coil, which has hundreds of turns of wire wrapped around that main line. It's that huge ratio of turns that just dramatically shrinks the current down.
But here's where it gets really interesting. In solving one problem, that massive current, we've accidentally created a new and potentially catastrophic one. This is what's known as the voltage paradox.
So the crucial thing to remember about any transformer is that there's this inverse relationship between current and voltage. It's a trade-off. If you drastically decrease one, the other one has to drastically increase to compensate. And when I say drastically, oh boy, I mean it.
Yeah, if we actually run the numbers through the standard transformer equation, taking a 400,000 volt line and then stepping the current down by a factor of hundreds, you could theoretically generate a potential of 80 million volts in that tiny little secondary coil. That is enough to cause a literal explosion and destroy everything nearby.
So how is this absolute disaster avoided? Well, the solution is beautifully, almost deceptively simple. The two terminals of the CT secondary coil are always connected to something. They are never, ever, under any circumstances, left as an open circuit.
This is one of the most critical, rule number 1, safety rules in any electrical substation. As long as that secondary coil is connected to a load, even if it's just a simple ammeter, the circuit is closed. This gives a current a low-resistance path to flow through, and that keeps the voltage down to just a few safe volts. But an open circuit, that would have near infinite resistance, and it would allow that terrifying 80 million volt potential to build up in an instant.
Okay, so we've safely figured out how to measure the current by stepping it way down. But what about that initial 400,000 volts? To tackle that, we need our second hero, the potential transformer, or PT, which is designed specifically to tame the voltage.
Now, the PT's job is way more direct than the CT's. It's designed to do one thing and do it with extreme accuracy. Take an incredibly high voltage from the line and scale it down to a standardized, safe level, usually around 110 volts, that can be easily read by any regular voltmeter. Simple as that.
Seeing them side by side like this really highlights just how different they are. To measure current, the CT has to be connected in series, so all of the electricity actually flows through it. But to measure voltage, the PT is connected in parallel, kind of just tapping into the line at a single point and comparing it to the ground. Two totally different jobs, two totally different connections.
So you might be thinking, hey, isn't this just a small version of those giant power transformers I see buzzing in substations? And yeah, they work on the same basic principle, but their purpose is completely different. A massive power transformer is like a freight train. It's designed to haul immense amounts of power.
A PT, on the other hand, is like a high-precision racing bike. It's not built for power at all. It's built for one thing: extreme accuracy. All right, so we've got these incredibly clever devices that give us nice, safe readings on a meter. But why go to all this trouble? It's not just about knowing the numbers. The answer? Well, it reveals the true critical purpose of the CT and PT. They are the grid's watchful eyes. This right here, this perfectly illustrates their real mission. The CT and PT aren't just measurement tools. They are the sensory organs, the eyes and ears of the power grid's automated protection system. When a fault happens, like a lightning strike or a short circuit, they instantly detect that dangerous surge in current or voltage. That information gets fed to protective relays, which are basically super smart switches, and those relays instantly trigger massive circuit breakers to cut the power, isolate the fault, and prevent catastrophic equipment damage and widespread blackouts. So, the next time you see a big transmission tower, you'll know about these silent, ingenious guardians that are constantly watching over it.